Hello, everyone. My name is Andrei Satarin, and I'm going to be talking about the paper understanding and detecting software upgrade failures in distributed systems. So let's go. Rough outline of the talk. I'm going to give an introduction of the paper, talk about findings they have on severity and root causes of upgrade failures. Talk about testing and detecting those failures, some conclusions, and in the end, I'm going to give some personal experience of me doing upgrade testing for the distributed system. So let's start with introduction. What are upgrade failures? In the paper, I describe them as failures that occur during upgrade. So it's not some configuration change. It's not a bug in a new version of software you just deployed. It's specifically the bug between interacting two versions of software during upgrade and nothing else. So why are they important? They looked at several distributed systems, and overall important aspects of those failures were that they are large scale because they touch either a large part of the system or the whole system, and upgrades usually move pretty quickly through the system. So any bugs in there are impacting the entire system. Upgrade itself is a disruption to the system normal operations, puts it in a vulnerable state. An impact of the bugs during the upgrade could be persistent, so you can corrupt the data and you need to do something about it later, which kind of costly. And overall, those are hard to expose in-house. There's probably little focus on testing for those upgrade failures for distributed systems in general. So what did they look at? They looked at symptoms and severity of upgrade failures, whatever root causes of those failures are, conditions, how to trigger them, and like why are they even happening. And the final goal is basically how to detect those failures for distributed systems and prevent them from happening in production. So these are the systems they analyzed. These are basically the bugs they looked at from the bug trackers of corresponding systems. Overall, it's about 100 bugs, more than that even. And this is where all the findings come from just basically, I assume, just reading and understanding those bugs. So let's talk about findings they have on severity and root causes and some other aspects of those failures. First of all, these are significantly higher priority than usual failures. So if you take a population of all the bugs in your system, percentage of higher priority bug will be lower than specifically for upgrade failures. So that, again, corresponds to their importance. And we kind of implies that we need to invest more in those. Majority of those failures are catastrophic. So it's either impacting the entire cluster or leads to catastrophic data loss, or maybe even performance degradation. And that's, again, compared to general population of bugs, it is much higher percentage. Those bugs during upgrades are easy to observe. Doesn't mean they're easy to find. It just means if you can drive the system into that behavior, have a workload, to drive the system into that behavior, you will observe some things like crashes or fatal exceptions or the whole cluster unavailability, which is kind of hard to miss in test, as long as you can actually have a workload and can drive system into that behavior. And even though they're easy to observe, 63% of them are not caught before the release. So the whole premise of the paper is we need to get better at testing for those upgrades, and we need to come up with some other solutions to find those before they make it to release, which authors are working towards. About 2/3 of those are upgrade failures are caused by data syntax or semantics, and those are roughly split 6-4 between persistent data and network messages. And 2/3 of those are pure syntax, and 1/3 is semantic difference. So even though the syntax of the data stays the same, it just interpreted differently between different versions. That comes later when they try to address those issues. So some percentage of those syntax incompatibilities are coming from serialization libraries. So things like protobuf or thrift, where you just describe the message in a special language, and that means you can automatically detect those incompatibilities versus trying to build some kind of a solution for every way to serializing. So that makes it easier to scale in terms of like if you build solution for Protobuf for Thrift, you can apply it to a lot of different systems, which they did. I'll later talk about that. In general, with all the upgrade failures they look at, none of them require more than 3 nodes. So 3 nodes is enough to trigger all the upgrade failures in all the systems they look at. And that corresponds to some other finding from a also good paper on general defects in distributed systems, which is called Simple Testing Can Prevent Most Critical Failures. Pretty well-known paper from 2014, where they found that 98% of all the failures in distributed systems are guaranteed to be observed on no more than 3 nodes. So that's an important result and kind of makes it easier for us to test. We don't need large clusters or anything like that. Almost all of those upgrade failures are deterministic, so you don't need to find any kind of special data races or timing conditions or things like that. If you can drive system into that behavior with the workload, you can observe those with pretty high confidence. So the next part of the paper is kind of testing and detecting how currently systems approach the testing for upgrade failures and how authors propose to do that in a more systematic way. So the limitations in the state of the art of the system they looked at, they noticed is that there's a problem with workload generation. So every time someone tries to test for upgrades, they design a workload from scratch. They don't reuse it from somewhere else. And that's kind of bad because you're trying to come up with a new workload. That means you kind of either doing it twice or not exposing the system to a variety of workloads during upgrade. Also, they noticed that there is no mechanism to systematically explore the whole space of upgrades, which includes different versions, different configurations, different update scenarios, which is like either stopping full stop upgrade or rolling upgrade. So those are not exposed in a systematic way. And their proposed solution is 2 tools. First of those tools is DUPTester. So DUPTester is a distributed system upgrade tester. The way it works, it simulates 3-node cluster. So you, as one of the findings mentioned, you just need 3 nodes and systematically test 3 scenarios. So like the 3 scenarios are kind of built in there. It's full stop upgrade, rolling upgrade, and adding new node to the system. As I mentioned before, the workload challenge, and they mentioned that in the paper specifically, that the main challenge is the workload challenge. So the way the DUPTester works with this challenge is they have 2 approaches. First of all is reusing stress tests, and that's relatively straightforward. You just run your system in a DUPTester in a containerized environment across 3 nodes, and you run your stress tests against that system while DUPTester exercises upgrades in a systematic way, and you look for all those crashes or catastrophic failures and things like that, which are hard to miss. The other approach is using unit tests, and there are some tricks, and I'm going to be talking about them in a second. So what's with the unit tests? The way they propose to reuse unit tests in a DUPTester, they have 2 strategies to use them. First of all is automatically translate the unit test in a client-side script. So if you have some test, this is kind of like why I put unit test in quotes, because to me that heavily implies that those unit tests are not actually unit tests. They're tests exercising system at a pretty high level, very close to its public API or external API. And this is why you can translate them into client-side scripts. So they're like more integration or end-to-end tests, if you will. So this is why we can translate. So the example they give is Cassandra unit test, where it exercises some operations and you can translate them. In their case, in DUPTester, it's Python. So they actually translate Java into Python, making those tests in Python. So this is why there are no guarantees to translate all of your unit tests. And it needs help from developers to map those functions, including internal API to external API, and also functions from basically Java into Python. Another strategy is to execute unit tests on version 1 of software, and then try to start it on version 2, which to me also implies they're not exactly unit tests, because first of all, they persist data. and also they expose. Again, they work at some kind of API where that persistence actually makes sense, and not some internal things which are not translatable and not guaranteed between the versions. The next tool they talk about is DUPChecker, which is targeting specifically syntax of data in the system for serialization libraries and enum types. So DUPChecker targets two types of syntax incompatibilities in the system. Specifically syntax, not semantics, of the data, and just two types. But those turn out to be enough to cover a lot of ground. So first of all is serialization libraries. So they try to compare serialization syntax definitions of basically protobuf definitions of your data across different versions, and they're all open source alternatives. So this, they mentioned that. And the other, a little bit more elaborate approach is enum typed data. I'll talk about both in a second. So for serialization libraries, for example, for protobuf, they basically parse protobuf definitions across two versions and have a set of rules to check that those definitions between two versions do not have any incompatibilities. For example, adding or removing required field in one of the versions will cause system to exhibit failure during upgrade if that code actually gets executed. So they found those and report them as bugs. With enums, it's a little bit more elaborate. They actually use data flow analysis across the program to find enums which get persisted. In this case, that's for Java. In this particular case, they mentioned for Java and for specific API to like write Java data. And then if there are any additions or deletions to those enums, and indexes of those enums get persisted. So not just string representation, but the index of enum itself and all the things they can find from data flow analysis. If both those conditions are true, they again report it as error to developers. So this covers enum specifically. So overall conclusions from the paper say, first of all, this is a first in-depth analysis, as long as like authors are aware, and as I'm aware, of upgrade failures in distributed systems. And they found like that those failures have severe consequences compared to general bug population. They developed the DUPTester tool and found 20 new upgrade failures in 4 systems. And DUPChecker found around 800, more than 800 incompatibilities across 7 systems. And 2 of those systems confirmed that all of those incompatibilities actually bugs, but they don't provide number, what the number was for those. And specifically, Apache Edge-based team requested DUPChecker to be a part of their overall testing pipeline. So they want to prevent those incompatibilities in the future. With that, I kind of want to transition from discussing the paper to my personal experience and commentary in the paper about upgrade testing. So first of all, they don't I guess talk a lot about correctness on the upgrade path because reusing stress tests or reusing unit tests where they say run it on version 1 and start it on version 2 does not imply that the results the system returns in those scenarios actually get validated that they're correct. So traditionally, stress tests don't have correctness validation. So because we imply that the system works correctly, we're interested in its performance. Also, correctness for distributed systems specifically implies correctness with failures. In the testing scenario, it means failure injection. In the real world, it means nodes failing, networks failing, things like that. They also do not discuss a lot rollback. They mention it like for one bug, but I think testing system upgrade definitely implies testing rollback, because that's the other aspect of rolling out, like working the system actually in production and operating it. And that's kind of, to me, it's missing in that paper. So regarding correctness, if we look at the system as a black box with version 1 in there, all the nodes running and everything happening, everything working, system exposes some set of invariants to its customer, and there's no break. But if we actually add version 2 and do an upgrade, so this is like in this example, it's going to be a rolling upgrade. That means systems kind of looking differently internally, but for external observant, those same invariants system provides, they still hold, and system must guarantee those. Otherwise, because for external observer, they don't see difference between this version and this version. They don't know if you're deploying. At least like modern systems don't do that. You don't put a maintenance notice saying like we're gonna experience failures in the database. That's not like what systems strive to do these days. So for external observer, there is no difference. So basically, my point here is that invariants during upgrade and invariants during the normal operation are exactly the same. So it means you can actually reuse a correctness test you already have, presumably for the system like, for example, Cassandra, where you have correctness tests which are Jepsen-like with fault injection. You can reuse the same test to test the system as a black box the way Jepsen does it. And you don't need to use stress tests. And those tests, correctness tests, also guarantee that they also check for correctness behavior during execution. So if your system returns incorrect result during upgrade, not just crashes, not those 70% of easy to detect failures, but something more subtle like returning incorrect result, you can also detect those. Because you're using correctness tests which actually validate those, and also using fault injection, because this is what Jepsen-like tests do. The other aspect I mentioned before is upgrade and rollback. So we do need to, in real world, we do need to test both upgrade and rollback, because rollback is the operation that might happen, and arguably those code paths are getting exercised even less frequently. So it's more important to test them in some kind of adversarial conditions, like with failure injections. And also, because we're talking specifically about upgrade bugs, that means the probability of exposing those bugs, especially under failure injection, where the whole scenario becomes even more probabilistic than before, we need to have increased mixed version time, because that directly corresponds how many bugs we can expose. So like the more we can keep the system in the mixed version situation, where we have version 1 and version 2. I'm talking specifically about roll-in upgrade scenario, obviously, because full stop upgrade is less interesting. So we need to maximize that mixed version time. So the way I previously did upgrade testing in practice was have a basically infinite cycle of upgrades and rollbacks. So the system where system goes through all the states infinitely. Obviously, in practice, they're not infinite. You have some kind of time budget, like 24 hours or 48 hours or whatever your release cadence is, things like that. And these are the most important states in this. So you want to schedule those upgrades and rolling upgrades in a way that maximizes time of upgrade and rollback, where the system actually running 2 versions concurrently. And as I mentioned before, you can use not just stress tests, as the paper suggests, but also your correctness validation test with failure injection on that, because in real world, your failures in distributed system do not stop when you do upgrade, and they will happen, and you do need to exercise those code paths during an upgrade in both versions or mixed of versions, and things like that. So this is the kind of cycle of upgrade and rollback, where you test both upgrade and rollback operations between version 1 and version 2, and correctness during that execution. So overall, like that's kind of my additional conclusion. Number 2 is that there is certainly value in the research and in ideas presented in the paper. I like how they reuse stress tests, obviously. The findings are very valuable because they give quantitative data about upgrade failures compared to all the other bugs in the system. But I think there are additional ways where we can improve upgrade testing for distributed system versus compared to what they authors propose. And I think thinking of the system during upgrade as thinking of the system during normal operation is a valuable approach, like treating it as a black box with invariants the way Jepsen does. Is a valuable approach to testing, which is like a basically well-known thing as a black box testing in approach. With that, I thank you for your attention, and I'm open to discussion.